Okay, imagine this. You're standing right in front of a huge symphony orchestra.
Mm-hmm.
All those different instruments playing together, blending into this one massive sound.
Right. Incredibly complex.
How on earth would you even begin to pick out every single instrument, every note, every little vibration that's all mixed up in there?
Yeah. Seems almost impossible.
Or think about like a medical sensor. It collects just a few little data points from your heart, maybe.
Yeah.
How can doctors look at that and like instantly diagnose a condition?
It does seem like magic sometimes, doesn't it?
It really does. But it's not magic. It's actually the power of mathematical transform.
Ah, yes. The secret sauce.
Exactly. So today, we're taking a deep dive into some of these really fundamental, but let's be honest, often kind of misunderstood tools in science and engineering. We're talking Fourier, Laplace, and Z-transforms.
The big three, really.
We're going to try and demystify what they actually do, why they're so incredibly important, and, how they let us see these hidden bits inside signals, whether they're smooth waves or just discrete points of data.
Yeah, unlocking the hidden structure.
Think of this as your shortcut to understanding the secret language of signals.
A good way to put it.
So let's start right there. We're talking about transforms. In this context, what is that fundamental idea? It sounds a bit abstract.
Well, it's actually quite intuitive when you break it down. Essentially, it's about changing your perspective on a problem or a signal.
Changing perspective.
Yeah, shifting it from one way of looking at it, like how it behaves over time, to another way, like what frequencies make it up. And you do this to make the problem easier to analyze or solve.
Okay, like looking at the same object but from a different angle reveals different features.
Precisely. And what's truly remarkable, I think, is that you don't lose any information in the process.
Oh, really? Not at all?
Nope. You can always transform it back to the original signal. But by shifting domains time to frequency, for instance, you uncover patterns or components that were just, well, hidden before. It's basically about breaking down something complex, a complicated function, into simpler building blocks, often like oscillating functions, waves.
Right. Okay. That makes sense. Like taking apart a complex recipe to see all the base ingredients.
Exactly like that. A great analogy.
So for someone listening, why should they care about this? I mean, converting signals from one domain to another, what's the real-world punchline?
Oh, the relevance is just enormous. These transforms are absolutely crucial for almost everything technical.
Like what?
Like solving the differential equations that describe how bridges vibrate or circuits behave, designing the filters in your phone that, cut out noise, analyzing audio signals, medical data like ECGs or MRIs, understanding vibrations. It's everywhere.
Wow.
It's fundamentally about taking really hard mathematical problems and turning them into easier ones, usually algebraic ones.
Turning calculus into algebra, almost.
In many cases, yes. That's a huge part of the appeal, especially for Laplace and Z-transforms.
Okay, so let's start our journey with probably the most famous name here, Fourier.
Fourier. Can't talk signals without him.
Let's begin with the Fourier series. So imagine you've got a signal that repeats perfectly, like the hum from a transformer or a perfectly held musical note. How do you dissect that?
Right. The Fourier series is the tool specifically for those periodic signals, the repeating ones.
Okay.
What it does is it decomposes or breaks down that repeating signal into a sum of simple sine and cosine waves. These are its fundamental frequency components.
The harmonics, right, I've heard that term.
Exactly, the harmonics. And the series gives you these numbers, coefficients, that tell you precisely how much of each specific harmonic frequency is present in that original repeating signal.
So it's like a frequency recipe for the sound.
Perfectly put. And, this core idea isn't even super new. You can find early forms of harmonic series way back in ancient Babylonian math. They used it for astronomical cycles.
No way, really?
Yeah. And even the Greek Ptolemaic system, with its deference and epicycles trying to model planet movements. That was kind of a related idea, breaking complex motion into simpler circles.
Huh. I never made that connection.
Then, later on, mathematicians like Clairaut and Lagrange did crucial groundwork. But what Fourier did, the really game-changing part, was provide the mathematical proof that any well-behaved periodic signal could be represented this way.
Ah, the universality of it.
Precisely. It gave us this universal language for periodic things, and that's used everywhere now. Electrical engineering, acoustics, electronics, signal processing, even quantum mechanics relies on these ideas.
Okay, that's powerful for repeating stuff, finding the hidden notes, like you said.
Yeah.
But What if the signal doesn't repeat? Most things in the real world don't, right? Like me speaking now, or a car driving past.
That's the million-dollar question, isn't it?
Yeah.
And that leads us directly to the Fourier transform.
Okay, the FT.
The FT is the generalization. It extends the idea beyond just periodic signals to handle any well-behaved signal, repeating or not.
How does it do that?
Instead of breaking it into discrete harmonics like the series does, the Fourier transform decomposes the signal into a continuous spectrum of frequencies.
Continuous, so like potentially infinite frequencies.
Well, a continuous range. It tells you the amount or amplitude and phase of every possible frequency component that makes up the signal, not just integer multiples of a fundamental. Think of it as a much finer resolution frequency fingerprint.
Okay, a fingerprint for any signal's frequency content.
Exactly. And crucially, just like the series, it's reversible. No information lost. You can take the frequency spectrum and perfectly reconstruct the original time signal.
And that's using things like MRI. You mentioned that.
Absolutely. The Fourier inversion formula is basically the mathematical engine behind reconstructing images in MRI. It takes the frequency-encoded signals from the scanner and transforms them back into a spatial image.
Wow.
You see it in forensics, too, like with FTI or spectroscopy.
FTO.
Yeah, Fourier transform infrared. It shines infrared light through a substance, measures the result, and uses the Fourier transform to very quickly figure out the frequencies absorbed.
Yeah, that gives a unique chemical fingerprint to identify the material. Incredible. Same math, very different applications. So the FT is great for continuous signals, but we live in a digital world now. Everything's sampled, right?
Yeah.
Discrete points, bits and bytes. How do we use these ideas there?
Right, that's the next crucial step. Bridging the gap to the digital domain.
Okay.
Theoretically, there's something called the discrete time Fourier transform, the DTFT. It's like the conceptual equivalent for signals that are discrete in time-sampled signals.
Oh, okay, so that's the answer.
Well, yes and no. The DTFT gives you the frequency representation, but the catch is the resulting frequency spectrum is continuous.
Ah, so infinite points in the frequency domain, hard to compute.
Exactly. Computing it perfectly would generally take infinite operations.
Yeah.
So for practical computation, we use the discrete Fourier transform, the DFT.
The DFT, okay, that sounds more practical.
It is. The DFT is designed for signals that are not only discrete in time, but also finite in duration, meaning you have a limited number of samples, which is always true in a computer.
Yeah.
The DFT takes those finite number of time samples and gives you a finite number of discrete frequency components back.
Okay, discrete time in, discrete frequency out. That sounds computable.
It is definitely computable. The calculation itself is straightforward. Now, interpreting the DFT results sometimes needs care because mathematically, it implicitly treats your finite signal as if it were repeating periodically.
Ah, okay. A slight wrinkle.
A slight wrinkle, but for many applications like digital filtering or just measuring the main frequency components in a data chink, it's the workhorse. It's incredibly useful.
You said the DFT computation is straightforward, so why do we always hear about the fast Fourier transform, the FFT? If DFT is easy, why need fast?
Ah, that is a fantastic question. Straightforward doesn't mean fast when dealing with lots of data.
Okay.
See, calculating the DFT directly, using its basic formula, requires a number of complex multiplications and additions that goes up with the square of the number of data points n squared.
N squared. So if you double the data points, it takes 4 times as long.
Exactly. For small n, that's no big deal. But imagine analyzing audio or radar signals or images with thousands, millions, even billions of points. N squared becomes astronomically slow, impractical for real-time stuff.
Okay, I see the problem.
This is where the FFT comes in. It is a truly revolutionary algorithm.
The famous FFT.
The very same. It's not a different transform mathematically. It's a family of incredibly clever algorithms that compute the exact same DFT result, but way, way faster.
How much faster?
Instead of n squared operations, the FFT typically takes around n times the logarithm base 2 of n operations. N log n.
N log n versus n squared. That sounds like a big difference.
It's colossal.
Yeah.
You mentioned earlier, for a signal with, say, n4096 points, which isn't huge by modern standards, the FFT is roughly 300 times faster than a direct DFT.
300 times, wow.
Yeah. This massive computational saving, largely brought to the mainstream by Cooley and Tukey in the 1960s, is what fundamentally enabled the entire field of digital signal processing as we know it.
So without the FFT?
So much would be impossible. Real-time digital audio, fast internet modems using OFDM, modern medical imaging, efficient data compression, countless things we take for granted rely on the FFT's speed.
Like the heart rate variability example you mentioned.
Precisely. HRV analysis takes the beat-to-beat interval data from an ECG, which can be thousands of points long. The FFT transforms that time domain data into the frequency domain almost instantly. Doctors can then look at the power in different frequency bands, low frequency, high frequency, and that tells them about the balance of the autonomic nervous system, assessing cardiac health, stress levels, even predicting risk. Doing that with a direct DFT would be way too slow for practical clinical use.
The FFT really did change everything then.
Absolutely, a computational breakthrough.
Okay, so Fourier, DFT, FFT, they're all about breaking signals down into frequencies. Fantastic tools. But what if our main goal isn't just seeing the frequencies, but understanding how a whole system behaves over time, especially like when it's starting up or reacting to a sudden input, the transient stuff?
Right. That's where the perspective needs to shift a bit, and where the Laplace transform becomes incredibly powerful.
Laplace. Okay. How does that differ?
The Laplace transform is designed primarily for analyzing continuous time systems, particularly those described by linear differential equations. Fourier is great for steady-state frequencies, but Laplace handles the whole picture, including initial conditions and transient responses.
How does it work? What's it transform to?
It takes a function of time, ft, and transforms it into a function of a complex variable, usually called s. So you go from the time domain to the s domain, or complex frequency domain.
Complex frequency. S.
Yeah, s is a complex number, often written as sigma plus j omega, or I omega. The omega part relates to frequency, like in Fourier, but the sigma part relates to damping or growth rates over time. This is key for analyzing stability.
Ah, so it captures more than just oscillation frequency.
Exactly. And its real superpower is how it handles differential equations. The Laplace transform has properties that turn differentiation and integration in the time domain into simple multiplication and division by s in the s domain.
Wait, it turns calculus into algebra?
Pretty much. That's the magic. It converts complex linear differential equations into algebraic equations in s, which are much, much easier to solve.
That sounds incredibly useful for engineers.
Oh, it is. It's a cornerstone of control theory, circuit analysis, mechanical system modeling. It's named after Pierre-Simon Laplace, who used similar math, actually for probability theory and diffusion problems, way back.
So it has deep roots, too.
Very deep. And because the transform results in what mathematicians call an analytic function in the complex plane, you can use powerful tools from complex analysis to understand system behavior like stability, pole zero analysis, things that tell you if the system will oscillate or decay or blow up.
Can you connect it back to Fourier at all?
You can. If you set the real part of s sigma to 0, so s just equals j omega, the Laplace transform essentially becomes the Fourier transform for many signals. But Laplace is more general because it handles that growth decay component, sigma, and works better for signals that don't start at minus infinity, incorporating initial conditions naturally.
Got it. More general for system analysis.
And they have neat tricks like the initial value theorem and final value theorem. These let you find the system's output right at the beginning, time 0, or its long-term steady-state value, time infinity, directly from the S-domain representation without having to fully transform back to time. Huge shortcuts.
Very practical. Okay, so Laplace is the go-to for continuous systems, differential equations, stability, transients. What about the digital world again? If we have discrete systems described by difference equations instead of differential ones.
Excellent question. And the answer is the Z-transform.
The Z-transform, the discrete counterpart to Laplace.
Exactly. It does for discrete time signals and systems what the Laplace transform does for continuous time ones. It's the fundamental tool for analyzing linear, time-invariant, discrete systems.
So it takes difference equations
and turns them into algebraic equations, but this time in the Z domain. The variable Z here is also complex, and it plays a role analogous to as in the Laplace domain.
And it's used for similar things, but in digital.
Absolutely. It's indispensable in digital signal processing for designing and analyzing digital filters. You hear about FIR filters, finite impulse response, and IIR filters, infinite impulse response. The Z-transform is key to designing both. It's also vital in digital control systems and for determining the stability of discrete systems.
Stability again. How does that work with Z?
Similar concept to Laplace, but the stability criterion is different. For a discrete system to be stable, all the poles of its Z-transform points, where the transform blows up, must lie inside the unit circle in the complex Z-plane.
Inside the unit circle. Oh,
This brings up a really crucial point about the Z-transform, something unique to it in Laplace.
What's that?
The transform itself isn't uniquely defined just by the mathematical formula. You also need to specify its region of convergence, or ROC.
Region of convergence, ROC.
Yes, it's the set of complex Z's values. for which the infinite summation in the Z-transform definition actually converges to a finite value. Different signals can actually have the same mathematical expression for their Z-transform, but different ROCs.
Whoa, so the ROC is part of the answer.
It's essential. The ROC tells you fundamental properties about the signal or system. For example, it determines if a system is causal, meaning the output only depends on present and past inputs, not future ones. For a causal system, the ROC must be outside some circle. It also determines stability. A stable system's ROC must include the unit circle.
So without the ROC, the Z-transform is ambiguous.
Exactly. It's a critical piece of the puzzle.
Right.
And yes, the Z-transform is directly related to Laplace. You can formally map the continuous plane to the discrete Z-plane using methods like the bilinear transform, which lets you, for instance, design an analog filter using Laplace techniques, and then convert it into an equivalent digital filter using the Z-transform. It really bridges the continuous and discrete worlds.
Wow. Okay, that is a lot of transforms. We've covered Fourier series, Fourier transform, DFT, FFT, Laplace, Z-transform. My head's spinning slightly.
It is a lot, but they all fit together.
To help wrap our heads around it, could you maybe give us the quick takeaway? If someone's looking at a signal or a system problem, how do they pick the right tool from this amazing toolbox?
Sure, let's try a quick summary. It really boils down to two main questions. Is your signal continuous or discrete? And are you primarily interested in frequency content or in system behavior, like stability, transients, solving differential difference equations?
Okay.
So if you have a continuous periodic signal and want its discrete frequency components, harmonics, use the Fourier series, FS.
Got it. Periodic, continuous FFS.
If you have any continuous signal, periodic or not, and want its continuous frequency spectrum, use the Fourier transform, FT. Great for general frequency analysis.
Okay. Any continuous FFT.
Now, for discrete time signals, theoretically, the discrete time Fourier transform, BTFT, gives you its continuous periodic frequency spectrum. But it's not directly computable, usually.
The theoretical one.
Right. For practical computation on finite duration discrete time signals, you use the discrete Fourier transform, DFT. It gives you discrete frequency components back.
Practical, discrete, master DFT.
And remember, the fast Fourier transform, FFT, isn't a transform itself, but a super-fast algorithm to compute the DFT. Use it whenever you need to compute a DFT efficiently, especially for large data sets.
Algorithm for DFT, FFT. Makes sense.
Okay, shifting gears to system analysis. If you have a continuous time system described by differential equations, and you care about transients, stability, initial conditions, use the Laplace transform, LT. It moves you to the complex S domain.
Continuous systems, diff EQ SLT.
And finally, if you have a discrete time system described by difference equations, think digital filters, digital control, and need to analyze it, use the Z-transform, ZA. It's the discrete equivalent of Laplace moving you to the Z domain, and you need that region of convergence.
Discrete systems, diff EQ's discrete cousin Nash and ZT with ROC.
You got it. That's the landscape in a nutshell.
That is incredibly helpful. What an amazing journey through this world of signal transforms. It's mind-blowing to think how these mathematical ideas connect things like ancient astronomy, modern medicine like MRI, and the digital music we listen to every single day.
It really is. These tools allow us to see structure and simplicity hidden within apparent complexity.
They truly let us see the unseen, quantify the unquantifiable.
Well put.
So for everyone listening, the next time you stream a video, listen to a perfectly clear digital song, or even just make a phone call. Take a second to consider these invisible, powerful transformations working constantly behind the scenes.
Humming away silently.
And it makes you wonder, doesn't it, what other complex things in our daily lives, or even in science or nature, might be hiding simpler, elegant patterns, just waiting for the right mathematical lens, the right transform, perhaps, to reveal them.